Today, I would like to talk about A-star search. A-star search is a kind of searching algorithm that makes use of heuristics to search for the shortest path. Before introducing A-star search, I would like to talk about Dijkstra's algorithm briefly. If you are already familiar with it, just take it as a short review. Dijkstra's algorithm is a classical algorithm that used for searching the shortest path in a graph. To implement Dijkstra's algorithm, we need to set infinite as the initial value to all the nodes in the graph, and set the start node to 0. Then we can start the search. Given a node with its designated value, we need to update all the values of its neighbors according to the weight of the edge between them. If the sum of the starting node value and the edge weight is smaller than the end node value, we will update the value of end node and mark this edge. After we update all the nodes, we generate a minimal spanning tree and can easily find the shortest path. One problem of this algorithm is that if there's a large number of nodes, the data structure designed for keeping the node's value will be large and redundant, since we only want to find the shortest path instead of the minimal spanning tree. Therefore, keeping track of the nodes that cannot be part of the solution seems to be unnecessary. Here, we introduce uniform cost search. It basically is the same as Dijkstra's algorithm, except that ECE will use a frontier and only keeps track of the nodes and values that we have explored. In each searching loop, it will explore from the node with smallest value which is popped out from the frontier. The searching ends when we find the goal. Having known Dijkstra's algorithm and ECE, we're only one step away from A-star search. The basic idea is, since we know the goal we are searching for, why don't we try to move toward it? Therefore, instead of only keeping track of the distance we have already traveled, we also want to estimate how far we are away from our goal. The estimation of the cost from current state to goal is called heuristic. And to move from ECE to A-star search, we need to save the value we have traveled to reach the node plus the heuristic of the node. So, how to choose a good heuristic? The most important thing is that the heuristic must be admissible. That is to say, the estimation must be smaller or equal to the real value. This will guarantee to find the shortest path to the goal. Usually, we will take Manhattan distance or Euclidean distance as valid heuristics in searching problems. I'm going to further explain how A-star search works in robot motion planning. Say we have a robot arm with 2 joints. We want the robot arm to reach a goal, while several obstacles are in its way. We can use A-star search in its joint space to find the shortest path. To be specific, first, we need to represent the problem in joint space and establish the graph to perform search on. Then, given the start point, we would explore its neighbors by keeping track of moved distance, calculating heuristic using Euclidean distance and push the sum to the frontier. Also, to retrace the path, we have to keep track of the parent node at each update. At each round, we would pop the node with the smallest value out as the new node to explore. After we reached the goal, we would retrace the parent nodes and generate a path in joint space. This would be the shortest path to reach the goal. That's all I want to share about A-star search. If you want to learn more, ECE448/CS440 Artificial Intelligence is a good course to take. Thanks for watching.